Hi there, I'm Ankash and I'm here to give you a presentation on atomic clocks and how GPS uses atomic clocks as an intrinsic part of the whole system. So, what's the first question that pops to your mind is what is an atomic clock? As Wikipedia would tell you, an atomic clock is a device that uses hyperfine transition frequency in the microwave or electron transition frequency in the optical or ultraviolet region of the electromagnetic spectrum of atoms as a frequency standard for its timekeeping element. Atomic clocks have been found to be the most accurate time and frequency standards known to man and are used as a primary means for international time distribution services for controlling the wave frequency of television broadcasts and in global navigation systems like the GPS, which for us is the topic at hand. But all that said, what does this mean? What is an atomic clock and how does it work? So, atomic clock, a dissection. Let us get an idea of how atomic clock works. This starts with the whole idea of electronic transitions. We have an idea that electrons occupy only certain allowed energy levels inside an atom. Any transition between them is corresponding to a specific frequency which usually lies in the ultraviolet or the visible light region. But there comes in another part of atomic structure that we have not yet discovered. This involves the fine structure splitting and the hyperfine structure splitting of the atom. Our focus here would be on hyperfine structure splitting of the atoms. What is hyperfine structure? Small shifts in splitting in the energy levels due to interaction between the state of the nucleus and the state of the electron clouds, which is, in case of atoms, this arises from nuclear magnetic dipole moment interacting with the magnetic field generated by the electrons and the nuclear electric quadrupole moment in the electric field gradient due to the distribution of the charge in an atom. These are different from fine structure in the sense that fine structure results from interaction between the magnetic moments associated with the electron's spin and the orbital angular momentum of the electron. This gives us a picture of how hyperfine structure splitting and fine structure splitting vary from one another. The energy associated with hyperfine structure splitting is orders of magnitude lower than that of fine structure splitting. Hyperfine structure splitting forms the basis of our atomic clock. Any transition between these levels so created by the hyperfine structure splitting results in an associated frequency that lies in the microwave region. Before we delve deeper into how an atomic clock works, let's take a step back and look at how an atomic clock came into being. Lord Kelvin was the first to propose in 1879 that atomic transitions could be used to measure time. It was the magnetic resonance theory came up by Isidor Rabi that in the 1930s that provided a practical method to make it happen. In 1945, Rabi suggested that we could use atomic beam magnetic resonance to form the basis for a clock. The first atomic clock was an ammonia absorption line created at the US National Bureau of Standards, which turned out to be less accurate than it was. The first cesium-133 atomic clock was built by John Essence and Jack Parry in 1955. This turned out to be the first accurate atomic clock. This led to a redefinition of second in 1967. So what is a second? As defined by the International Standard of Unit, the second is the duration of 9,192,631,770 periods of radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. This definition refers to a cesium atom at rest at a temperature of 0 Kelvin. Thus, an atomic clock helps define the standard of timekeeping, a second, to be the time that it takes a cesium-133 atom in a defined state to oscillate 9,192,631,770 times. This brings us to the question at hand. What makes the atomic clock tick? In an atomic clock, first the atoms are heated in an oven and bundled into a beam. Each atom has one of the two possible energy states. They are referred to as hyperfine levels, but let's call them state A and state B. A magnetic field then removes all atoms in state A from the beam, and so only atoms in state A remain. The state A atoms are sent through a resonator where they are subject to microwave radiation, which triggers some of the atoms to change to state B. Behind the resonator, the atoms that are still in state A are removed by a second magnetic field. A detector then counts the atoms that have changed to state B. The percentage of atoms that change their state while passing through the resonator depends on the frequency of the microwave radiation. The more it is in sync with the inherent oscillation frequency of the atoms, the more atoms change their state. The goal is to perfectly tune the microwave frequency to the oscillation of the atoms and then measure it. After exactly 9,192,631,770 oscillations, a second has passed. Now let's come back to our topic at hand, and GPS and how it works. GPS works on the concept of trilateration. Let me give you a simple example to understand the concept of trilateration. Let us suppose that you are lost in the middle of nowhere and you don't know how to find your location. You ask someone and they tell you that you are 625 miles outside of Boise, Idaho. That gives you a whole circle of possible regions and you do not know where on that circle you lie on. You ask someone else and they give you the information that you are 690 miles from Minneapolis, Minnesota. This leads you to provide another circle that intersects at the previous circle at two different points and thus narrows down the possibility of where you are. Then you further go on to ask someone else who gives you the information that you are 615 miles from Tucson, Arizona. The three circles converge at one point, that is Denver, and now you know where you are. This same concept applies to the concept of GPS in a global scale. Instead of circles, we'll be using spheres, and the intersection of these spheres results in two different points, out of which one lies on the earth and the other outside. Thus we know which one to eliminate, and we have our location on the basis of the concept of trilateration. This brings us to the topic GPS and atomic clocks. The first GPS systems developed by Keir and Wyffenbach was based on the Doppler effect by determining the position of the frequency changes of the satellite's broadcast signals. The mini-track system, as it was called, compared different angles of incoming radio signals and paired antennas. This process required a precise time scale to synchronize the transmitted and received signals. So in 1964, Roger Easton realized that by putting a clock on the satellites, a single source could transmit time to both the transmitter and receiver. Space-based timing led to a new generation of GPS with high-precision atomic clocks placed on each satellite. Without atomic clocks, such a generation of GPS would not be possible. So how the pieces fit together? A pseudo-random code is simultaneously run from the transmitter and the receiver. When the transmitter's signal reaches the receiver, by then there is a time lag created. This time lag gives us the time that it took the transmitted signal to reach the receiver. Assuming that the signal traveled in a straight line, the speed of light multiplied with this time lag gives us the distance of the receiver from a specific satellite. In order to make this measurement happen, the receiver and the satellite both need clocks that can be synchronized down to the nanosecond. To make a satellite positioning system using only synchronized clocks, you would need to have atomic clocks not only on the satellite but also on the receiver itself. But atomic clocks cost somewhere between $50,000 to $100,000, which makes them just a bit too expensive for everyday consumer use. The global positioning system has a clever, effective solution to this problem. Every satellite contains an expensive atomic clock, but the receiver uses an ordinary quartz clock, which constantly resets. In a nutshell, the receiver looks at incoming signals from 4 or more satellites and gauges its own inaccuracy. In other words, there is only one value of the current time that the receiver can use. The correct time value will cause all the signals the receiver is receiving to align at a single point in space. That time value is the time value held by the atomic clock in all of the satellites. So the receiver sets its clock to that time value, and it then has the same time value that all atomic clocks in all of the satellites have. The GPS receiver gets atomic clock accuracy for free. When you measure the distance to 4 located satellites, you can draw 4 spheres that all intersect at one point. 3 spheres will intersect even if your numbers are way off, but 4 spheres will not intersect at one point if you are measured incorrectly. Since the receiver makes all the distance measurements using its own built-in clock, the distances will all probably be incorrect. The receiver can easily calculate the necessary adjustments that will cause the four spheres to intersect at one point. Based on this, it resets its clock to be in sync with the satellite's atomic clock. The receiver does this constantly whenever it's on, which means it's nearly as accurate as the expensive atomic clock in the satellites. In order for the distance information to be of any use, the receiver also has to know where the satellites are. This isn't particularly difficult because the satellites travel in very high and predictable orbits, and the GPS receiver simply stores an almanac that tells it every satellite should be at any given time. Even if there are slight variations in the satellite, the Department of Defense constantly monitors their exact positions and transmits any adjustment to all the GPS receivers as part of the satellite signal. A constellation of satellites. These images here show the various satellites that orbit the Earth and are a part of the global positioning system. There are proposed to be in total of 24 satellites going around 3 different orbits. While there has been some slight modifications, and now there are 6 planar orbits and 4 satellites in each orbit. There is a planned proposition to enhance the number by providing higher number of satellites and more number of orbital paths. Let's come to competing technologies. Some of the competing technologies existing worldwide are Beidou, system developed and operated by the People's Republic of China, initiating global services in 2019. Galileo, a global positioning system developed by the European Union and other partner countries, which began operation in 2016 and is expected to be fully deployed by 2020. GLONASS, Russia's global navigation system, which is fully operational worldwide, serves as a means to enhance GPS rather than exactly compete against it. IRNS is a regional navigation system developed by the Indian Space Research Organization. QZSS is a regional navigation system receivable in the Asia-Oceanic regions with a focus on Japan. Some of the common occurring bugs that we see in GPS is that the path and the speed of the signal are hindered by large objects by the skyscrapers, which deflect the light and increase the time lag. Then there is Earth's atmosphere, which causes the speed of the signal to vary. These could result in a change in the value of the time lag and hence result in a variation in the accuracy of the GPS. The solution to is differential GPS that helps correct these errors. The basic idea is to gauge the GPS inaccuracy at a stationary station with a known location. Since the DGPS hardware at the station already knows its position, it can easily calculate its own inaccuracy. The station then broadcasts a radio signal to all DGPS equipment in the area, providing signal correction information for that area. In general, access to this correction information makes DGPS receivers much more accurate than ordinary receivers. Another problem we face with GPS receivers is that the GPS receiver, if it loses connection with the GPS satellites, then it loses connection with the hyper-accurate atomic clock. This results in us being untethered and lost. The solution is in works at the University of Sussex, where researchers are trying to develop a way to dramatically reduce the size of the comb by integrating it with a tiny chip. With that, let us come to the future prospects. First, we see NIST physicist Andrew Ludlow and his colleagues achieve a new atomic clock which has performance records in a comparison of 2 ytterbium optical lattice clocks. On the right, we see an atomic clock that could pave the way for autonomous deep space travel that was successfully activated last week and is ready to begin its year-long tech demo. The mission team confirmed this on Friday, August 23, 2019. Which brings us to the end of this presentation, and I hope you enjoyed it and have a nice day.